All right, we are live. Let me move that a little bit so that way the camera's not, the microphone's not too close to me. So yeah, welcome on in everyone to Monday's edition of Calculus Live. I am Robert, the AP Math Guy, and tonight we are going to be talking about this thing called continuity. So as people are joining in, let's see those likes. And I'm going to start waving at people as they join in. So welcome on in, driver, and thank you for the likes. So I will go ahead and wave at you all. And on the off chance, hey Hefe, how's it going? Thank you for the love of our likes. And like I said, tonight we are talking about continuity. I'm going to give people a moment to jump in here before we get started. Happy Monday to you as well, Hefe. How was it? How was your Monday? Hopefully it was good. It was all right. My Calc kids have their first quiz tomorrow on limit graphs. How do you think it's going to go? You think it's going to go well? I think they understood it. Awesome. Hopefully it does. I can't wait to hear about it. And how it went. Indeed. But yes, in case I can't wave at you because for some reason TikTok won't let me, I'll wave at you now on camera. Yes, math. Yes, KG. So, tonight, like I said before, we're going to talk about something that I think is really important, especially when we get into when we do get into derivatives, and that is this idea of a limit. Or not a limit. Good job, Robert. Let's try that again, shall we? We're not even 4 minutes in, and already I'm making mistakes. But hey, you know what? Such is life sometimes, yes? So let me try that again. So continuity, there we go. Let's go ahead and talk about what it is. So first, it would help if we define continuity. So when we talk about continuity, we're talking about if a function is continuous or not. So I'm going to start by writing this down. So a function, and yes, I did switch to graph paper tonight because I feel like I'm going to be drawing a few graphs and it's going to be easier if I draw it on this paper versus the plain paper. Hey Vivid, how's it going? Welcome on in. A function f of x is continuous. Might help if I spell continuous right, or make it look like I can spell continuous. I just started derivatives. I'm doing so good at it. That's awesome, Vivid. I'm really happy to hear that. I am really happy to hear that. Way to go. Is continuous at x equals a. And let a be any point in the function. It doesn't have a doesn't have to be a specific point, but it can be any point on that function if it meets these three conditions. I hope I spaced them out enough. So here we go. Everything I feel is going to be easy until integrals, then I'm going to die. You're not going to get to integrals for a little while. I think you're going to get into integrals sometime in January. Yeah, so at least for me, when I took AP Calc, we got to integrals around late January, early February. Yeah. The biggest things I would watch out for right now, Vivid, is going to be when we talk about related rates and optimization, because those are word problem heavy problems. But I think I have it on my list that we're going to talk about optimization at some point here soon. So, as I was saying, a function is continuous at a point A if it meets these three conditions. So first, the point f of a has to be defined. Second, the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x. And third, the limit as x approaches a of f of x must equal f of a. So if all three of these conditions are met, then our function is continuous at that point. Make sure you understand how and when to use, and difference between intermediate value, mean value, and extreme value theorem, What is a limit? Like, how is it defined? So, remember, actually, I have it right here. So a limit tells me as x gets infinitely close to a point A, what y value are we approaching? So that is a limit. It's just asking, as x gets closer to a certain point, what is y getting closer to? Epsilon delta, we might do the epsilon delta proofs, but I haven't. But right now I want to keep it relatively simple. So the way I tell my students, let's say we're looking at a graph. The way I tell my students about continuity is this: if I can draw the function without lifting my pencil at a point, then the function is continuous at that point. If I have to lift my pencil to continue, then it is not continuous at that point. Now, there are going to be times when we won't be able to see the graph, but there will be times where it will say, hey, given this graph, is there any point, is the function continuous at this point? Prove that get propulsion equation is derived from force equals mass times acceleration. I haven't done physics in years. Are you going to do intermediate value theorem soon? Yeah, I can definitely add that to the list. Let me go ahead and find that list. I think at this point I might need a new note card for the list. That's weird. Anyway, I'll definitely add it to the list. Thank you, Cotton, for the follow. ln x and e to the x. Okay. Corners. I'm not necessarily sure what you mean by corners, Kevin. Hey, Beast, how's it going? Welcome on in. So, let's start with a couple of examples of problems where we're going to take a look at the graph. Thank you, Mr. 705, for the follow. So, let's take a look at a graph. And I apologize for corners aren't differentiable, but they are continuous. Yes. That's right, Hefe. But we're not talking about differentiability tonight. We are just talking about continuity. So, I think the middle is going to be about there. It looks to be about the middle. And I'm going to be drawing a little bit tonight, so I apologize in advance if my drawings are terrible. So, let's go ahead and draw our first function. So let's say, I'm going to start off with a little bit of an easy one. I have a math degree, appreciate you teaching me. No problem. I'm really happy to hear that. If infinity isn't the delineation. I'm not really quite sure what that means, but teaching on here, awesome. Yeah, so let me go ahead and draw a function. And I know I do this one a lot, but it's a fun function to draw. I work as an actuary but miss pure math. I actually considered working as an actuary, and I actually took the P exam, but I failed. I'm thinking about trying again. Nice cubic, definitely. Though, thank you, Catalina, for the follow. So here, let me pick a point A. Let's pick here. Let's let that be A. So, my question is the following. Is the function continuous at A, at x equals A? Well, let's go ahead and find out. So let's run it through my 3 tests and see if it meets all 3 criteria. So first, f of A is defined. So here, I'm looking for an open dot or something where I have a vertical asymptote. But at A, do you see a circle there or no? I failed P 3 times, been doing exams since 2018. Okay. Yeah, I took it once, failed it. I'm thinking though of trying again. I'm thinking of trying again. I'm aiming for the spring of next year. It's not because I'm gonna switch to become an actuary. I just want to see if I can pass it. Because I think I know where I went wrong the first time. Back then I wasn't really doing math as much, so I forgot a lot of the calculus and statistics that go into it. But since then, I've relearned a lot of stuff. So I think I might be able to pass. But like I said, I'm going to try it again just because I can. But yeah, so at A, I don't see a circle or an open dot, nor do I see a vertical asymptote here. So so we know that the function is defined at that point. Now, let's look at number 2. Does the left side limit equal the right side limit? So, if I take my limit as x approaches a from both the left and the right, as I approach from the left here, I'm approaching this point, which I'm going to call f of a. So I'm going to say that f of a is about right there. I'm going to eyeball it. Thank you, Kevin, for the follow. So the left side limit approaches f of a, and if I approach from the right, I'm also approaching f of a. So we know that this second condition is met. So that's a check. The third condition is that the true limit equals f of a. Is that the case? Does the limit as x approaches a of f of x equal f of a? Bro giving me PTSD with this Calc 1 stuff. I took it in 2018. Okay. I apologize for the PTSD, but I think that now that you're not taking it as a class, or maybe you are, I'm not sure, but if you're not, it will give you the opportunity to just sit back and relax and enjoy the math. Yeah, it does. So remember that if the left side limit equals the right side limit, then the true limit exists. And since my limit is equal to f of a, as we saw here, this third condition is met. So, thank you, Akira, for the follow. Dude, the last time I took calc was in 2008. Fair enough. The last time I took a calculus class I took one, was 2013? No. Yeah, 2013. But yeah, you're absolutely right. It does. So because all three conditions are met, the function is continuous at x equals a. What does the limit mean? Okay, so the limit tells me as x gets really, really close to a, what is the y value that it approaches? Or that doesn't make grammatical sense. Let's try that again. As x gets closer and closer to a from both sides, what value does y approach? So remember, this is x. If my pen. So the other reason why I decided to try graph paper tonight was because I wanted to see how my pen wrote on it. Apparently, it's not doing as well as I thought it would. There we go. So that is what the limit means. Excuse me. So let's try another one. Let me go ahead and draw a new graph. So I will use this one. And again, for these, I'm going to try and draw these halfway decently, but I can't make any promises. Luckily for me, this is math and not art class. Oh boy. I might have to get the new pen out. There we go. Do you think it's good that I finished unit 4 of Calculus BC before school starts, or is it too much? That depends. How much time did you spend getting to that point? Was it 1 week, or was it since June? If it was thank you, Josuet, for the rose, and I'm apologize if I pronounced that incorrectly. I'm more than sure that I did. So yeah, but thank you. About a month. Okay. A week a unit, that's stretching it, but so if a function at f of a had an open circle, would that point be undefined? Yeah, so it would depend on whether it was defined elsewhere. Oh, yeah. No, you're right. I misread your question. Yeah, I think it is time for a new pen. Um, Actually, that's weird. It works on my note cards, but let me try moving it down onto the table. So I'm going to go ahead and try and draw a different function. So let's say, what shall I draw? Let's draw this. So I'll draw a line that looks like that. And then we'll do that. And I want to know is this function continuous at x equals a? What do you think? Is this function continuous at a? Yeah, no, it wouldn't. It definitely would not pass the horizontal line tests. But if it's not the only, in order to tell it's not a function, it would have to, it would, so functions pass the vertical line test, but if they fail the horizontal line test, it means there's no inverse. Again, because I have a straight line followed by what appears to be a negative upside down parabola, this tells me that it's probably more than likely a piecewise function. Where we switch from straight line to parabola. But again, for these, I'm just drawing random functions. Yeah, for some reason it must not like that point or that edge. But yeah, so let me zoom in. There we go. So is my function continuous at this point right here? Yes or no? What do you think? Mark says yes. Hefe says yes. So, in order to tell whether it's continuous or not, let's put it through our checklist and see what happens. So, first one on the list, f of a is defined. Well, here it looks like it's defined. Why? Because I don't see an open dot here, nor do I see a vertical asymptote. So it is defined there, so we can check that off the list. Second, does the limit from the left as x approaches a equal the limit from the right as x approaches a? So let me approach a from both the left and the right. So if I approach a from the left, it looks like I'm approaching that point right there. And if I approach from the right, it also looks like I'm approaching from there. So we can check that because that is the case. And see if does the limit of the function as x approaches a equal the value of y at a. Well, again, I don't see any open dots, so it does indeed. So we can check that off our list. And since all three of these conditions have been met, our function is continuous at A. Yeah, it must not so I had it kind of propped up on my computer, so it must not have liked that. Awesome. So, let's go ahead and continue from here. Oh, sorry, Josette. I meant 2 roses. It only showed me 1 for some reason. But yeah, thank you for the 2 roses. I don't know if you're still here or not, but if you are, thank you so much. So let's try one more of these where I attempt to draw a graph. And then I will show you I'm going to show you these things called discontinuities. Or maybe I will now. Let's see. Thank you, Law, for the follow. Alright, let me try and draw this. Try being the operative word. Ooh, that doesn't sound good. Is this calculus? Indeed it is, Arnold. Indeed it is. Yeah. Maybe it is time for me to use a new pen on this. Let me go ahead and do that. I'll save this pen for... So now, let's go ahead and draw another function. I'm going to try and be a little more creative this time. Rather than do my usual or that. Let me see. Let's try the following. Maybe this pen's not going to work either. You're learning discontinuities tomorrow? Awesome. Awesome timing. So, you came to the right place. When teaching pre-algebra, what's your best approach? What is the first thing you think of? You first focus on. Sorry about that. So I actually haven't taught pre-algebra in a few years. But one thing. So usually the first month, I usually like to review for like the first 3 weeks or so, just to make sure that we are ready for, yes, integer fluency is definitely a topic, but yeah, so I make sure that we're able to do the basics, and make sure that our integer fluency, as Hefe said, is good to go. So let's go ahead and give this a try. So I'm gonna say, here's A. So, let's go ahead and find whether whether my function is continuous at x equals A. What do you think? Yes or no? Mr. 705 says no. Meaty Lift says yes. Okay. With two question marks. Okay. So, let's go through our checklist and see if it is continuous. So, first, is f of a defined at, is f of x defined at a? Well, I have a closed dot up here. Thank you, Travel and Eat, for the follow. And also, great name, by the way. Two things that I like to do. Travel and Eat. So yeah, my f of a is defined here. So I'm going to call that f of a. So that's a check. And then, does the limit as x approaches a from the left equal the limit as x approaches a from the right of f of x? Let's see. So, as I approach f of x from, as I approach a from the left, I'm approaching here. And if I approach from the right, I also approach here. So that is a check. Now, the third question, does the limit equal the value of f of a? Well, here's our limit, and here is our f of a. These two are not equal, because if they were, we would have the same, this would be all the way down here, or vice versa if our limit was up here. So because it does not meet that third criteria, so we can put an x there, because it doesn't meet this criteria here, our function is not continuous at x equals a. I don't remember if I thanked you for this, but thank you, Tyler, for the rose. So, we can see that, so it's kind of like that analogy I had of lifting the pencil, right? So, I draw the function, and then when I get here, I'm not allowed to cross this open dot. So what do I have to do? I have to lift my pen and go here. And because I have to lift my pen, the function is not continuous there. But then I also have to jump back down here and continue. So this function is not continuous at a. So not continuous. Continuous at the point x equals a. Maybe it's not the pens. Maybe it's the paper. Thank you, Sammy, for the follow. I legit cried during this section in math. I'm sorry to hear that. Well, hopefully tonight you don't cry. Or at least not because of this. Hopefully you don't cry at all, but yeah, so what I'm going to do, let me try one more pen, and if it doesn't really work on here, then I'm going to switch back to my original pad. So, I'll get this. Thank you, Carter, for the follow. What's going on here? Good question, Javier. We are talking about continuity. I'm just starting Calc 1 this semester. I'm liking it a lot. I hear Calc 2 is where I'll cry, though. So, Calc 2, I would say, is overall more difficult than Calc 1. But if you understand a lot of the concepts in Calc 2, you'll be perfectly fine. You'll be good to go for Calc. Or, if you do well in Calc 1, you should be good to go for Calc 2. Yes, that's what I meant to say. Thank you, Fairy Tales, for the follow. Just started Calc AB. Nice to see some content on it. Yeah, for some reason, there's not a lot of calculus on here. So hopefully, my goal is to bring calculus and the other AP classes as well to TikTok. Thank you, Rafi, for the follow. Calc 2 has lots of integration? Absolutely. So with that, I have this written down on a note card, so we can refer to this note card for the rest of our problems tonight. So let's go ahead and turn the page. So here is our criteria of when a function is continuous. If you want to take a moment, maybe take a screenshot of it or write it down. And while we do that, let's see if we can't get to 3K likes before the next problem. I know you can do it. You're only 600 away. There we go. Thank you, Sammy, for the rose. 2 roses. 3, 4, 5, 6, 8, 9. Wow. Thank you so much for the 13 roses. So, yeah, so like I said, it's really shocking, or I think it's kind of shocking that we don't have that there's not a lot of calculus here on TikTok, or at least I haven't been able to find it. And there's 3K. So I'm going to go ahead and leave this up, or I'm going to put it down here for a moment while I show you. You can only get through Cal 1 and Cal 2 if you have a good professor. I think you can get through Calc 1 and Calc 2 without that. You just have to have someone help you with it. But I do tend to agree with the fact that having a good Calc 2 professor and Calc 1 professor, or even teacher, definitely helps. So I'm going to move that over there for now. And so I want to show you something. So let me go ahead and draw another graph. Thank you, Drive World Clips, for the share. Yes, if you know someone who could benefit from joining tonight's live, feel free to share it to them. So, let me go ahead and attempt to draw this. Oh, that's going to work. Thank you, Nah, for the follow. So I think middle's going to be about there. Oh, this pen is going to work well tonight. X, Y. Hopefully it doesn't dry out, though. Alright, so here I'm going to draw another function, but this time I'm going to purposefully cause some discontinuity. Thank you, Drive World's Clip, for the rose. I almost missed it. So here I'm going to have a straight line with that there. So, here, this is a piecewise function. Very good. But I'm drawing it to show you the 3 different types of discontinuities that we can run into. Thank you, Tavo, for the follow. So, here, there are 3 different types of discontinuity, and I'm going to show you how each one occurs. So, 3 types of let's see if I can spell continuity. Continuities. There we go. Perfect. So, there are 3 types of discontinuities that we're going to look at tonight. First is what we call a removable discontinuity. Please don't die on me, pen. And where does a removable discontinuity occur? Well, just like the last problem, well, I don't necessarily know my scale here on my x value, but so a removable discontinuity occurs. So this occurs when, yeah, this pen's starting to die on me too a little bit. So I might have to break up the new one. The one thing about these pens that I don't like is the little plastic tip that you have to remove. There we go. I think I got it. There we go. So this occurs when the limit as x approaches a of f of x does not equal f of a. For example, thank you, he's talking to you for the follow. So for example, here, the limit exists, but the function does not exist at that point. So this whole, that is a removable discontinuity. I'm just gonna call it 1 for space. And then we have our second type of discontinuity, and that is called a jump discontinuity. Or, as I like discontinuity. I have the word in front of me. You'd think I would be able to spell it right given that I can see it, but apparently I can't. Thank you, he's talking to you, for correcting me on the spelling. Nuity. So, a jump discontinuity, or, as I like to call it, I like to call the jump discontinuity the Van Halen discontinuity. So, for those of you who are fans of rock and roll from the 80s, I think it came out in the 80s. 70s or 80s, I'm not sure, no. Now I have to look it up. You would think if I referenced it, I would at least know when it came out. Yeah, 1984 it came out. This gave me PTSD. I just graduated with a degree in math, and I'm trying to chill on TikTok. Okay. Well, you found the right place. I'm not going. So, like I tell people all the time, when I teach, I don't like to put a lot of pressure on people. I'm trying to go for a nice relaxing time with math, because that's how math should be done. It should be done at a good pace, kind of like solving a crossword puzzle with the New York Times, or a Sudoku puzzle. If you want to time yourself, go for it. But I find that when you go nice and slow with math, you make less mistakes. Thank you, BS Detective, for giving me that. I'm glad I could help with your lesson, indeed. So, like that, the reason why I like to call it the Van Halen is because in 1984 they released a song called Jump. I'm not sure if I can play it without triggering the copyright, so I'm not going to, but it's a good song. Thank you, Eduardo, for the follow. So this discontinuity occurs when my true limit does not exist. So the limit as x approaches a from the left. This is a brand new pen. Maybe it's the paper that doesn't like it. Does not equal the limit as x approaches a from the right. Yeah, I think it's the paper. I'm not necessarily sure it was the pen, because this is a brand new pen and it's struggling to write on this f of x. But that is how you know I'm alive, because if I weren't, I wouldn't allow me to write like that. So here, as you can see here, as I approach this point, let's call it B. Let's call this point B. So as I approach B from the left, my y value approaches this open dot, but as I approach from the right, y approaches this closed dot. So because the one-sided limits are not equal, this tells me that I have a jump discontinuity, or I'm going to keep calling it the Van Halen discontinuity. There's another popular song. I forget who it is. It's my University of Wisconsin football fans will know it. It's Jump Around. So if you want, another way we can remember the jump discontinuity. And then third is what we call the infinite discontinuity. We can also call it a non-removable discontinuity. There we go. After about 10 times of writing this tonight, I might still get the spelling wrong. So, an infinite discontinuity is one where I have a vertical asymptote. So, this occurs when the limit as x approaches a from the right of f of x is equal to plus or minus infinity. Thank you, Landon, for the follow. And or the limit as x approaches a from the left of f of x is equal, yep, it's definitely the paper, plus or minus infinity. And we see that it looks like we have a vertical asymptote here at this point. Let's call it C. C. So when x is C, it looks like I have a vertical asymptote. So therefore, this is an infinite discontinuity. So those are the three different types of discontinuities that we're going to see tonight. There's a fourth one that's called an oscillating discontinuity, and that happens when we essentially have something like this going on. I'm going to try and draw it. It's kind of hard to draw, but basically, an oscillating discontinuity, I can draw a axis better than that. So let me draw it. I'll give it its own special graph. because again, it's kind of hard to draw on this. It would be kind of hard to draw on that graph. So I had something like this going on, and then as I get closer, it just goes wild and crazy. So this is my best attempt at drawing what the oscillating discontinuity looks like. As I said before, I apologize for the awful drawings, because let's face it, I'm not a very good artist sometimes. But that is my best attempt at drawing the oscillating discontinuity. So basically, as we get closer and closer to a point, it oscillates between one point and another so fast that we can't tell exactly what the value would be at that point. So this is an oscillating discontinuity. Let me write that down. Let me see if I can spell oscillating. Discontinuity. Is that still a function? Believe it or not, I think it is. But it it definitely wouldn't have what was I going to say? Anyway, I think it still is a function, believe it or not. It's just really hard to determine what the actual value would be. Again, we're not going to see this tonight. Or this will be the only time you see it tonight. Because from here, we're going to start finding discontinuities algebraically. So we're going to use these three things and our list, our checklist, which I have here, for the next few problems, or for the rest of the evening. Example is the graph of 1 over sine x. Yep. Or sine of 1 over x. Did I say 1x? I meant 1 over x. So yeah, if I graphed 1 over x... Oh, that's right, my calculator decided not to work, and I don't quite know what's wrong with it. Because no matter what I press, it's not doing anything. Oh. Tan is stuck. That'll explain it. I had to get the tan button unstuck. There we go. So if I graph, or if I attempt to graph sine of 1 over x, it's not going to graph anything because I didn't write anything in. 1 divided by x. Yeah, see how it kind of oscillates here? We wouldn't be it wouldn't be continuous at the point where it's oscillating. Second plus 712. I'm not sure. But yeah. So again, we're not going to run too much into the oscillating discontinuity tonight. So I have this here, and I also have it as a note card here. Thank you, Carl, for the follow. So I'm going to refer to these two note cards. And because it looks like the paper's not really liking the pens that I'm using, I'm going to switch paper. And I'm going to go back to here. You have a question? Shoot. When you multiply it by x, does it become removable? Are you talking about sine of 1 over sine? Or sine of 1 over x? If it is, let's find out. So if I multiply it by x, 1 over x, graph. Yes, sine x is removable. So yeah, so the question is, it would be removable if the limit of the function didn't actually equal the value of the function. So the limit, as we saw when we did the squeeze theorem, the limit of x times sine of x as x approaches 0 is 0. But when I plug it, or sine of 1 over x, right? So limit as x approaches 0 of, actually, let me show you. Because we just did it last night, I think. Last night or the night before. Nope, it was last night. So, it was... Yeah, so, like this problem that we did last night, if I find the limit as x approaches 0 of x times sine of 1 over x, well, we discovered last night that through the squeeze theorem, this limit would be 0. Even if I'm multiplying by x, it would still be 0. So, yes, the limit would exist, but the function would not exist, right, because of this 1 over x here. And as a result, then yes, it would be a removable discontinuity. Can we study infinite things with math? Yeah, of course we can. Some of that math I don't know, but can we use mathematics to study something infinite like the universe itself? Yeah. Physics involves math. All the sciences involve math. I forget who said it, but someone said that mathematics is the queen of all the sciences. I know there was another, I think it was, science is the queen of all the disciplines, but math is the queen of all the sciences. I think that's how the saying went. You're a fourth-year PhD candidate at LSU. Congratulations. What's your dissertation going to be on? Stochastic analysis. Cool. What is that? Modeling random processes. Okay, cool. That's really cool. So, let's go ahead and use our next and do our next example. So, I have the following. F of x is equal to what? To 4x plus 5 over 9 minus 3x. And I want to know if it's continuous at the following points. And if it's not continuous, what type of discontinuity do we have? So let's find out whether our functions are continuous here or not. And again, if they aren't, then we need to figure out what type of discontinuity it is. So let's start with this first one. A function f is continuous at x equals a if all three of these conditions are met. So let's start with this x equals 1. If I plug in 1 for x, am I going to run into division by 0? What do you think? If I plug in 1 for x here and here, do I have division by 0? Yeah, right. I do not have division by 0. So 1 is true. So I'll circle it here. What about 0? If I plug in 0 for x, do I have division by 0? Thank you, Nash, for the follow. User says no. Aiden says yes. Michael says no. Fatty says no. And I apologize if I pronounced that incorrectly. But what happens if I plug in 0? I get 4 times 0 is 0. And 0 plus 5 gives me 5. And then 9 minus 3 times 0. 3 times 0 is 0. 9 minus 0 is 9. So I get 5 over 9. So no. This function would be continuous. Or not necessarily continuous, but defined. What about 3? If I plug in 3 for x, what do I get? Do I get division by 0? User says not defined. Fadi says yes. Hefe says yes. Michael says yes. Yeah. So if I plug in 0, I get what? I get 4. Or yes, good job, Robert. Let's try that again. If I plug in 3, there we go. I get 4 times 3 is 12. 12 plus 5 is 17. And then 9 minus 3 times 3. 3 times 3 is 9. 9 minus 9 is 0. Thank you. I think that's KLIMN for the share. So yeah, so this function is not defined. So we know automatically that it's not continuous. Because in order for it to be continuous, remember, it has to meet all 3 of those conditions. Not continuous. So I'll save finding what type of discontinuity we have there until later. I'm not sure if it's a jump discontinuity or a movable discontinuity or an infinite discontinuity. But let's test 2 and 3. So we want to know, does the true limit exist as x gets closer and closer to 1? So let's test that. So if any polynomial of degree greater than 0 is in the denominator, there's a 0, assuming we allow complex numbers. Is that necessarily true? It sounds right. Yeah. So, I'm thinking negatives for some reason. Yeah, no, that sounds right. So here, I'm going to test the limit as x approaches 1 of that. So, limit. So, remember, this essentially says, does the true limit exist? So, the limit as x approaches 1 of 4x plus 5 all over 9 minus 3x. Well, here, I can try direct substitution and see if that will work. So that's going to give me 4 times 1 plus 5 over 9 minus 3 times 1. 4 times 1 is 4. 4 plus 5 is 9. 9 minus 3 times 1. 3 times 1 is 3. 9 minus 3 is 6. So that is going to equal 3 over 2. So yeah, so the limit does exist. So the true limit exists at that point. So I'm going to mark that down. as 2. And now I'm going to do the same thing for 0. Limit as x approaches 0 of 4x plus 5 over 9 minus 3x. If I plug in 0 here using direct substitution, we said earlier that it doesn't cause division by 0. So what would this equal? User says 5 over 9. Michael says 5 over 9. Yeah. So 4 times 0 is 4. 4 plus 5, 0 plus 5 is 5. And 3 times 0 is 0. 9 minus 0 is 9. So yeah. So this meets that criteria. Now for step 3. We need to find if the limit equals the actual value there. So here at 1, well, did I have to do any algebraic gymnastics to find this limit, or did I just have to use direct substitution? Well, I don't see algebraic gymnastics, so we can say for certain that this limit is equal to the value of x, or value of f of 1. So that is met. Therefore, because it meets all 3 conditions, this is continuous. What about 0? Does it meet the third requirement? Does the limit actually equal value of f of x at 0? User says sure. Well, let's find out. Did I have to do any algebraic gymnastics here to get 5 over 9? Or did I just have to plug in 0? Yeah, all I had to do was plug in 0, right? So because of that, we can say that those are equal, and therefore, because again, this met all 3, no gymnastics, yes. So because it meets all 3 of these conditions, this is continuous. Now, what type of discontinuity do I have here? Well, remember that it's going to be one of these 3. So a good way to test it is to test the limit. So, limit as x approaches 3. We'll start with the left side limit of 4x plus 5. Or actually, let's use that. 9 minus 3x. So, let's see what happens as I get closer and closer to 3 from the left. So, again, I'm going to use my table method. F of x and see if this approaches anything. So, I'm going to pick 2.9, 2.99, and 2.999. These points are smaller than 3, but close to 3. So what happens when I plug it in for x? So I have 4 times 2.9 plus 5 divided by 9 minus 3 times 2.9. I get 55.3 repeating. Hey, Dad, how's it going? So 55.3 repeating. Now if I plug in 2.99 plus 5 divided by 9 minus 3 times 2.99. I get 565.3 repeating. So we can see that I could do this point, but I think we can see that this is shooting towards positive infinity. But just for fun, let's check it out anyway. So 4 times 2.999. What is up with the camera? Let me readjust here. There we go. Plus 5 divided by 9 minus 3 times 2.999. Hey, hi, how's it going? Yeah, so we get 5,665.3 repeating. So 5665.3 repeating. So we can see that as we get infinitely close to 3, then it's shooting towards positive infinity. So remember that it has an infinite discontinuity if the limit, either from one side or both sides, as x approaches our value of f of x, is positive or negative infinity. And here, I have the limit as x approaches 3 of this. From the left, we're approaching infinity. So this is a infinite discontinuity. Awesome. Can you explain the 1 again? I missed it. No problem. So I assume you're talking about here? So remember that in order for a function, the first rule, okay. So first rule says that a function f is continuous if f is defined at a certain point. So here at 1, so when we talk about definition, in this case, we're looking for division by 0. If division by 0 happens at a point, then it is not defined. But when I plug in 1, I don't get division by 0. If I plug in 0, I don't get division by 0. But if I plug in 3, I do get division by 0 because 9 minus 9 is equal to 0. Good question, Naw. Good question indeed. Oh, okay, makes sense. Thank you. No problem. Always happy to help. Always happy to help. So now that we've tried one like this, let's go ahead and try some where we'll have to do a little bit of algebra. So let's say I'm going to give you a function that is discontinuous, and we're going to find the point where it's discontinuous using our list. Can you explain limits at infinity? Sure. I think I have that on my list somewhere of topics. So basically, actually, yeah, if I don't already have that topic on my list, I will add it now. Thank you, Rain Girl, for the follow. Where is the list? Just had it here. So there's that. So yeah, I still, I think I have to redo, I think I'm going to have to get a new unit circle. Thank you, user, for the follow. There we go. Huh. Yeah, I'll go ahead and add that to the list. Because we're dealing with limits, I might end up doing that here sooner rather than later. But yeah, so let's go ahead and do a couple more, and then we'll call it a day. So, here, I have f of x is equal to x squared minus 9 all over 3x squared plus 2x minus 8. So I'm going to tell you there is a discontinuity here. Where is it? And how are we going to find that discontinuity? Well, we could start and look through this list, or I could try and break this down as much as I can and maybe find an algebraic way to get a discontinuity. So let's go ahead and break this down a little bit. Up in the numerator, it looks like I have difference of squares. So how would I factor x squared minus 9? What math is this? This is calculus. Right, it's x plus 3x minus 3, right. So f of x on top, I'm going to have x plus 3 times x minus 3. And then, on the bottom, would you say calculus is like statistics? I probably would say they're two different disciplines. Calculus, statistics deals with a lot of word problems. Yeah, no, I wouldn't. Yeah, I agree. I wouldn't say it at all. They're two different disciplines. So here, I'm going to go ahead and factor, see if I can factor at least this. So what I'd like to do is I'm going to go ahead. This is intermediate algebra. Kind of. What I'm doing right now is intermediate algebra, but continuity is calculus. So, here, how would I break that down? Well, I'm going to find two numbers, multiplying to negative 24 and adding to 2. So that would be 1 and 24, or negative 20, negative. So I have negative 1 and 24, negative 2 and 12, and I know that it's negative, that the larger number is positive because of this sign here. No, don't do that, Mr. Dan. I appreciate the participation. Yes, please, no, don't ever feel like you need to shut up. That's not what yeah, 6 and 4, right? So, but it would be negative 4 and 6. So I have negative 4 and 6. So now I'm going to go ahead and use grouping. If you want to use another way to factor, go for it. So this I can rewrite as 3x squared plus 6x minus 4x minus 8. So here, on top I still have x plus 3x minus 3. And on the bottom, well, I can factor out a 3, right? Because I'm looking for greatest common. So I'm going to divide here. And I'm looking for the greatest common factor between 3x squared and 6x. And that would be 3x, yes? 3x. And here, 3x squared divided by 3x is x. And 6x divided by 3x is 2. And then here I can factor out a 4, or negative 4. Be left with x plus 2. And then I can factor one more time. So that is x plus 3, x minus 3, all over x plus 2. times 3x minus 4. So now, here's the next question. Let's go ahead and now test that. So now, are there any points here where I would have division by 0? Do we set it to 0 to find discontinuity? So we're going to go ahead and... So I'm looking for where we have division by 0. Okay, Michael, where are they? Yep, one is -2. Yep, and the other is 4/3. Right. Yes. So this is so we have discontinuities. Continuities at x plus 2 equals 0 and 3x minus 4 equals 0. Here, if x plus 2 equals 0, then x is -2. And if 3x plus minus 4 is equal to 0, then x will equal 4/3. So, those are where our two discontinuities occur. So, I can also tell you what type of discontinuity occurs here. Why? Because with this, if I have something that I can cross off in the numerator and in the denominator, then that will be where a removable discontinuity occurs. But since I can't do that, these two would be infinite discontinuities. Thank you, Ivan, for the follow. Thank you, Jeffrey, for the follow. Whoops, my error. No problem. Welcome on in. So if you can't cancel it's infinite discontinuities. Yes. That is correct. So a good candidate for us to working on my PhD in math, just learned something new. Awesome. Way to go. When is it an asymptote? So it's an asymptote when we have an infinite discontinuity. So for example, there will be if I were to plug this into my calculator, there would be a vertical asymptote here and a vertical asymptote here. In fact, let's plug that into Desmos and see what we get. Jumps are piecewise. Yep. So a good candidate for, if you see a piecewise function, then it's a good candidate for a jump discontinuity. So let me go ahead and open up Desmos for a moment, and let's see. Did I freeze? There we go. So, how often do you do these lives? I do them every night. So I have x squared. X squared, actually no, I need to put in parentheses. So I have x squared minus 9 all over 3x squared plus 2x minus 8. And there we are. So we have a vertical asymptote. I have a vertical asymptote here at x equals 2. And I have another one here. Brightness needs to go a little lower. Yeah, I can do that. So, get out of there. Brightness. Like that. Yeah, so we have a vertical asymptote here at 2. And we have one at 4/3. And yeah, it does appear we have a horizontal asymptote at 1/3. But that's going to be our infinite limits. So our infinite limits help us determine where horizontal asymptotes are if they exist. Yeah. Do they go in order of AP Calc units? Usually it's whatever either someone requests or whatever I am doing that night. So sometimes, like a couple weeks ago, I was doing lives on optimization, but tonight I wanted to go back and rewind a little bit. So I try to go in order, but sometimes that doesn't happen. But for the most part, I try to go in order. Yes, this would be Unit 1. Yep. So let's try a couple more. And then you'll go ahead and call it an evening. Thank you, Mango, for the follow. So what would the answer be if they equal each other? Thank you, Carlos, for the follow. What time do I usually do these? I do these at about 11:30 Eastern time. So what happened? So what would the answer have been if they equal each other? Are you talking about something like if this were like x plus 3 instead? The 2 and 4/3. So if these two are equal, then it would be then we would only have one discontinuity. Yeah, so we would only have one discontinuity at that point. Good question. Thank you, Jenny, for the follow. And I apologize if I pronounce that incorrectly. That one looks fun. Let's try another one. Let's just try another one. F of x is equal to x plus 3 all over x squared plus 5x plus 6. So let's go ahead and find if there are any discontinuities here. So what I'm going to do, I can't factor the top anymore, but I can factor the bottom. What would be my factors of this denominator? Naw says 2 and 3. Jeffrey said I meant x plus 2, x plus 3. Yeah, exactly. So I would have x plus 3. I'm going to write it this way. Thank you, YH, for sharing the live. X plus 2. So, here we go. Now, I'm going to put that in parentheses. Remember how in algebra we learned that things can't cancel if I'm adding or subtracting in the numerator or denominator? Well, that is mostly true. However, believe it or not, I can actually cancel an x plus 3 and an x plus 3 here. Why? Because I can rewrite x plus 3 as the following. I can rewrite it as 1 times x plus 3. So, here, because I'm now multiplying, I can go ahead and cancel here and here. There would be an asymptote at x equals negative 2. That's right. So we have an we have an asymptote. Asymptote at x equals negative 2. That's right. But there's another point where I have division by 0, and that's that x plus 3. However, I removed it by canceling it from the numerator. So, whenever I have this going on where I can cancel, or where I can reduce from both the numerator and the denominator, at this point here, where this is equal to 0, there will be sorry about that. There will be a removable discontinuity at that point because I'm essentially removing it from the function. So there's a whole at x plus 3 equals 0. If that's true, thank you, user. Thank you, Mango. So if x plus 3 equals 0, then x equals negative 3. So there is a whole at x equals negative 3, and there is an asymptote at x equals negative 2. And those are the only two discontinuities. It would be continuous everywhere else. If it asks for a discontinuity, would it just write the whole? Can you go over squeeze theorem and ILT theorem? Squeeze theorem, we actually did last night, Meg. But what level math is this? This is calculus. ILT theorem. I'm not quite. I have to look that up because I've heard it before, but I can't remember what it is. Inverse Laplace transform. Nope. So ILT is a different class entirely. ILT involves is differential equations. Did you mean IVT? Yeah, no problem. No problem at all. So, yeah, so IVT is intermediate value theorem. It connects with this, but tonight I just wanted to focus on continuity. But yeah, I'll do a live on IVT. Thank you, Gab, for the follow. In fact, I have 2 topics that I need to add to the list. So I can't quite place the list right now, but let me go ahead and write that down. Can you go over principal unit normal vectors? I can add that to the list too. So IVT. Do I think that discontinuity is cool? I do. I think it's fun. Principal unit normal vectors. And there's a third topic on here that thank you, Cool Breeze, for the follow. What is the most fun math? That is subjective. I personally love calculus. I think that it's one of my favorites. I also like this thing called abstract algebra. which is really kind of cool, though I haven't studied it in years, so I need to relearn it. But when I took it in college, it was kind of fun. Or no, it was fun. So I have a couple more problems, and then we will call it a day. So, so when the graph has an open circle, it's a removable, and when it's closed, it's infinite. Nope. If it's open, then it's a whole, but if it's closed at a point, then it's defined. So open dot. So open dot, so something like this. F of x, not defined. Whereas if I have something like this, with a closed dot, f of x is defined. What grade did you get in Calc 2? I got, oh, wow, it has been almost 15 years since I took Calculus 2, but I'm pretty sure, I know I got an A. I think I got like a 97 or 98. I don't remember the exact number, but it was somewhere in that realm. Then why is the open circle again there if it's not defined? Because it's there because if I were to draw a line, so these holes are actually, if we look at a graph, we can't actually see them at all with our eye. So we draw a hole here and not a hole here. So when I have a line like this, that means every point except for here is defined, whereas this is not the case. Term hole and removable discontinuity are the same, just use name different. Yes, that's correct. That would be correct. Because even with this hole at -3, if I plug in -3 here, I would get 0. I would get 0 over 0. What about Calc 3? That one I didn't do as well in. I think I got like a 82. Like I said, I don't have my I don't have my I don't want to call it report card, but I can't think of what else it's called, so I'll call it a report card. Yeah, so I don't have it right in front of me, so I couldn't tell you. I think I got a B in that class. B or B minus. Okay, nah. Well, we're not quite done yet. So I still have one or two problems. Show me some trig problems. Well, I will. I will give you some trig. Actually, no. Not this one. So, I'm going to give you a piecewise function. F of x is equal to the piecewise function of the following. Holes are removable. Yes. Jump and VAs are non-removable. Correct. So, let's say I have x squared minus 9 for x less than or equal to 3. And then I have (12) when x is greater, or nope, Wrong inequality. Greater than 3. And I want to know if there's a discontinuity here. And if there is, what type of discontinuity? So piecewise functions, as I said before, piecewise functions like this are good candidates for Van Halen's or jump discontinuities. But like I said, I like to call them Van Halen. Cue of Van Halen music. Like I said, I'm not sure if I can play it or not and not get not trigger copyright. I'll have to take a look into that. If I play like a 3-second snippet of it, will I get flagged? So, can I explain limit laws next? Yeah, I could include that in a future live. Oh, by the way, how are you, world? So here we know that we can see that there's no division by 0 here. So we know that this is always defined. Now, is there a true limit here? In other words, if we're going to test if this is a jump discontinuity or not, I want to find the limit. I want to find the left and the right side limit. So here, I'm going to start with the left side limit. Limit as x approaches 3 from the left of f of x. Well, which of these two am I going to use? Well, because I'm approaching from the left, I'm approaching from all values net. Yeah, good job. Let's try it again. Because I'm approaching from the left, I'm approaching from all values less than 3. And if, as you can see, when x is less than or equal to 3, I use this top function. So this would equal the limit as x approaches 3 of x squared minus 9. So I'm going to go ahead and use direct substitution here to find that limit. So I have 3 squared is 9, and 9 minus 9 is 0. So I need to find the right side limit. So limit as x approaches 3 from the right of f of x is going to equal, well, I'm going to use the greater function, right? Because when I approach from the right, I'm looking at all values greater than 3. And when x is greater than 3, y is going to be 12. Or f of x is 12. So I have limit as x approaches 3 from the right of 12. Well, the limit as x approaches any number of a constant is just that constant. Hey, lovely dimples, how are you? Welcome. So now, I want to know, does 0 equal 12? Thank you, Joel, for the follow. Does 0 equal 12? George says no. Yeah, no, it's not. At least last time I checked, 0 doesn't equal 12. So because these two are not equal, the true limit does not exist. And because the true limit does not exist, there is a jump discontinuity at x equals 3. Jump at x equals 3. And that is it. Any questions on that one? Any questions at all? I'll just wait until you do another one. No problem. I'm going to do one or two more, and then we will call it a night. Why didn't you check 1 and 3 as well? I did check 3. Oh, why didn't I check 1 and 3 on the list? Is that what you're talking about? Cool. So remember that in order for a function to be continuous, it has to meet all 3 of these criteria. And so, because it didn't meet the second criteria, it's already not continuous, so it doesn't make sense to check the other 2. So if it fails 1, stop. Right, yes. That's right. Thank you, Snake, for the follow. Thank you for the follow. Cool. So like I said, we'll try a couple more, and then we will be good for the evening. So it is now time to turn the page. And we shall see about the next problem. So before we get to the next problem, let's see if we can't get to 5K likes. Let's get to 5K before the next problem. So while you are liking the live, so like I said, I go live every night at 11:30 p.m. Eastern. So we are almost at 5K. And we're past 5K. Let's go. All right, so on to the next one. So this one, I'm going to give you a function, and I'm going to give you a point. And I want you to tell me if it's continuous at that point. So here we go. So f of x is equal to the following piecewise function. So I have 6x squared. Do I know any good resources for discrete math? None immediately come to mind, but oops, that should be an x. Over 2x minus 1, when x is 1/2. Or not equal to 1/2, excuse me. And then 7/2 when x is 1/2. And I want you to I want to know, is there a discontinuity at x equals 1/2? If yes, which one? Thank you to Minnie for the follow. So here, let's take a look at our checklist. So, first, we need to ask ourselves, is f of x defined at x equals 1/2? What do you think? Is f of x defined at x equals 1/2? What does discontinuity mean? Sure, so discontinuity means a break in the function. So basically, a function is discontinuous if when I draw a function, I have to lift my pen before I can continue drawing. Santiago says yes, Na says yes. Yeah, so it is defined, right? If I plug in 1/2 here, I would get 6 times 1/2 squared is 1/4. So that's going to be 6 times 1/4 is 6/4 plus 1, or yeah, plus 1/2. So 3/2 plus 1/2 is 2. 2 minus 2 is 0 over 2 times 1/2, which is 1. 1 minus 1 is 0. But if we look here, we see that x does not equal 1/2. Thank you, Liz, for the follow. Instead, when x equals 1/2, f of x is 7/2. So yes, it is defined. So we can check it off our list. So let's check that. Now, we need to know if the limit as x approaches a from the left is the same as the limit as x approaches, or I'm sorry, if limit as x approaches 1/2 from the left of f of x equals the limit as x approaches 1/2 from the right of f of x. So, remember that the limit doesn't actually care about what the value is at that point. So, because I don't have a less than or greater than sign in both of these, instead I have not equal here. That means when I take the left and right side limit, I'm going to use this top function. Because we're approaching values of 1/2 from both the left and from both numbers less than 1/2 and numbers greater than 1/2. So x equals 1/2. Well, if x is equal to 1/2, then it can't be greater than or less than 1/2. So I'm going to use this top function for a limit. So let's plug that in. I have limit as x approaches 1/2 from the left. Or actually, you know what? I remember that if the limit from the left equals the limit from the right, then we have the true limit existing. So I'm not going to take the limit from both the left and the right. I'm just going to take the limit and see what I get. So I have 6x squared plus x minus 2 all over 2x minus 1. So here, I need to do some algebra. So, do we have sorry, why am I forgetting what I'm saying? Let's try that again. So, yeah. So here, if I plug in 1/2, as I said before, I get 0 over 0. So I'm going to need to do some algebraic gymnastics here. So let's try factoring the top and see what we get. So I'm looking for values of that multiply to -12 and add to 1. So what are two numbers that multiply to -12 and add to 1? Four and -3, right. So, that's right. So here, I can rewrite this as the following. Limit as x approaches 1/2 of 6x squared minus 3x plus 4x minus 2 all over 2x minus 1. Thank you, KLIMN, for sharing the live. So from here, I'm going to go ahead and factor by grouping. So what is the greatest common factor of 6x squared and -3x? Yeah, it's 3x. So here, limit x equal x approaching 1/2 of 3x times what? Well, 6x squared divided by 3x gives me 2x. And 3x divided by 3, negative 3x divided by 3x is 1. Negative 1, excuse me. L'Hopital says 12 versus 3.5. Well, I'm not necessarily interested in taking the derivative here of the top and the bottom and finding that limit. But what I am interested in is, yes, I could do L'Hopital here. Yes, I could. But I want to show you how to do it this way in case we can't use L'Hopital. So now I have 4x and negative 2. What is the greatest common factor there? Yeah, it would be 2. Plus 2. And I'd be left with 4x divided by 2 is 2x. Negative 2 divided by 2 is negative 1. And that's going to be all over 2x minus 1. And then I can factor out 2x minus 1. Limit as x approaches 1/2 of 2x minus 1 times 3x plus 2. That's going to be all over 2x minus 1. So now, remember, I can rewrite 2x plus minus 1 as 1 times that quantity. And now I have a 2x minus 1 on top and a 2x minus 1 on the bottom, so I can cancel those. And finally, I have limit as x approaches 1/2 of 3x plus 2 over 1. I'm just going to write that as 3x plus 2. Now if I plug in 1/2, I have 3 times 1/2 plus 2. 3 times 1/2 gives me 3 halves. And 2, remember I can rewrite that as 4 halves, so I have 3 halves plus 4 halves. 3 plus 4 is 7 over 2. So that is our limit. So because the true limit exists, we know that the second condition has been satisfied. So that is a check. And finally, we need to know if the limit as x approaches 1/2 of f of x equals the value of f at 1/2. Here's the question. Does the limit equal the actual value? I'm glad you're finding these. I'm glad you're Santiago says, yeah. Yeah, so limit equals actual value. So the third, nope, wrong one. The third condition is met. All 3 conditions are met. So therefore, this function is continuous at 1/2. So if we answer, is there a discontinuity, would that be yes or no? Is there a discontinuity? Wayne says yes. George says yes. Okay. So remember, all 3 of our conditions are met. Right, Santiago. So there is not a discontinuity. So the answer is no discontinuity. So just because we see a piecewise function doesn't automatically mean that there's going to be a Van Halen discontinuity or jump discontinuity. We have to do the test and see if our conditions are met. If this one's not met, then it's a jump. If that one's not met, then it's a hole. Cool. So with that, let's go ahead and do the final problem of the night. Because we are going into 2 hours, which is awesome. So final problem. So there are 10 of us in here. I think 7K likes is doable for a final problem. So let's see if we can't get to 7K likes. I know you can do it. So while we're doing the while we're getting set for the final problem, hopefully everyone is having a fun time tonight. And like I said, my goal with these lives is to do math, but at a relaxing pace. And my other goal is to make you like math, even if it's just the tiniest bit more than when you walked in. If I do that, I'm not naive enough to think that one live and you're gonna all of a sudden love math if you really despise math. No. But I want you to like math at least maybe not even 1% more, but like maybe 0.01% more than you did when you walked in tonight. If that's the case, then I've done my job. If you like it more than that percentage, then that's awesome. As long as you don't hate math more than when you walked in. Because like I said, we're here to do math at a nice, relaxing pace. We're not here to do math we're not here to solve problems in like 5 seconds. Because sometimes the more we rush, the more mistakes we make. And that's the thing. It's okay to make mistakes. I'm not saying it's not. But I find that a lot of mistakes are made when we're rushing, when we're trying to do a problem as fast as we can. So cool. We are at 7.1K likes. So now, let's do the final problem. So, I'm going to give you another piecewise function for this one. But I'm going to change it up a little bit. I'm going to change up the problem a little bit. So, here we go. So f of x is equal to the following. So we have x squared plus 3x plus 2 all over x plus 2 when x is not equal to negative 2. And then some number k when x equals 2. So I'm going to give you this information. Or I'm going to ask you this question. What value of k makes f of x continuous at x equals negative 2? What value of k makes f of x continuous at x equals negative 2? So here, I'm given that this is a continuous function at x equals 2. But I want to know the value of k that makes this continuous. So here, I'm going to pull out my checklist again. And I know that all three of these conditions are met. So I know, based on the fact that it's asking what value of k makes it continuous, I know that f of negative 2 is defined. I might want to put a negative there. I know that the true limit exists at x equals 2. And I know that the limit is going to equal f of 2. I'm going to use this third one to figure it out. So, I would like you all to walk through with me on this problem. So first, I'm going to take the limit as, so I want to use this rule. I want limit as x approaches negative 2 of f of x to equal f of negative 2. So therefore, the limit as x approaches negative 2 of f of x is going to equal, what's f of negative 2? F of negative 2 is k. So, I want to solve, I'm going to solve for k here. So I'm going to plug in, because I'm approaching negative 2, I'm not looking at the values that are equal to negative 2. I'm looking for the values that approach from numbers both greater than and less than negative 2. So if x is equal to negative 2, then that's neither greater than nor less than. So I'm going to look at this top piece right here. So the k is going to equal the limit as x approaches negative 2 of my top function here. So I have x squared plus 3x plus 2 all over x plus 2. Can I factor that numerator? And if I can, what would it factor to? What would this factor to? Not the bottom, the top, the numerator. Santiago says x plus 1. Okay. I think you're a step ahead of me, Santiago. Right. Oh, you were completing your answer. Sorry about that. Yeah. So this, right, because I'm looking for two factors that multiply to 2 and add to 3. Well, 2 is a prime number, meaning that its only multiples are 1 in itself. Negative 2 of x plus 1 times x plus 2 all over x plus 2. From here, remember, x plus 2 is the same as 1 times x plus 2. What do I do now? What should I do from here? What do I do now? Cancel out? Okay. What would I cancel out now? What would I cancel out? You're right, but what would I cancel out? Right, I would cancel out an x plus 2. Why? Because I'm multiplying by x plus 1 by x plus 2 in the numerator, and I'm multiplying 1 by x plus 2 in the denominator. So because I have multiplication, thank you, Manif, for the follow. I can cancel out my x plus 2s. Thank you, Manif. I really appreciate that. So now, I can take the limit as x approaches 2 of negative 2, of what's left. Well, I have x plus 1 on top and 1 on the bottom. Anything divided by 1 is itself. Thank you, Santiago. Anything divided by 1 is itself, so I can just leave it as x plus 1. Now, can I plug in -2? Yeah, I can. So now, final question of the evening. If I plug in -2 for x, what would k equal? That's right, it's -1. So k is equal to -1. Thank you, Cherry Pie, for the follow. So yeah. Can you give us one more really hard one? I don't know. What do you think? Shall I do an encore problem? Thank you, Cherry Pie. Do you want an encore? One more. Encore. All right. Let's see. Do we if another person says we want to do an encore, we can do an encore. So does anyone else want an encore? I know Tim does. There it is. There's the second person, Tim. So at least 2 of you want an encore. You don't know what that means? Okay. So an encore, so when you go to a concert, a encore is basically when they play 1 or 2 more songs. So they leave the main band leaves the stage, and then after a few minutes, while everyone's chanting encore, they come back out on the stage and play 1 or 2 more songs. So that's what an encore is. All right, I will do an encore. I will just need a moment though to look up a problem. So while we wait, let's go ahead and get as many likes as we can. No problem, Santiago. Thank you for joining us. I don't know how hard we want to, how difficult we want it to be, while at the same time going over. Thank you, Tim, for the follow. So I'm going to try and look for a difficult one. That one looks kind of fun. That one also looks kind of fun. But would we know how to do that one? That one, maybe? Okay, yeah, I'm looking for one that I think would be challenging, but not impossible. Do you do derivatives and integrals here? Yes, I do. I do indeed, George. That one looks challenging, but not in. Okay. Let's go for it. We'll do another problem where I'm going to give you a piecewise function, and I will want you to tell me if it's discontinuous at that point. And if it is, where it's discontinuous. But I think I found one. So, f of x. Thank you, Rocco, for the follow. equals, or do I want to do that one? Let's do some trig. So I have x sine x if x is less than or equal to pi, and then I have x times tangent of x when x is greater than pi. Thank you, Anjo, for sharing the live. I'm not sure if that J is pronounced like an H or a Thank you, S Checo S10 for the follow. So, and I want you to tell me, is this function continuous at x equals pi? So, let's go through our checklist one more time, because we will need it for this last problem. First, does it meet the first condition? So a function f of x is continuous at x equals a if one f of a is defined, 2, the left side limit equals the right side limit at that point, and 3, if the limit as x approaches a, if the true limit is equal to f of a. Also, if not, which discontinuity? Continuity. Oh, there's not another n. So, what do you think, Tim? Is that difficult enough? Let's see if you're right. So first, I want to know if f of pi is defined. So if I plug in pi, I'm looking, remember, f of a is defined means that I need to pick the point that has x greater, or x equals pi. Which one am I going to use? Am I going to use this top one, or am I going to use this bottom one for part 1? Tim says top. Yeah, it is the top one. Yeah, so I am going to use this top one. Why? Because for this top one, x is less than or equal to pi. So when I'm looking for whether f of a is defined or not, I'm looking for where x equals my value of interest. And here, x equals pi, so I'm going to use this top function. So I'm going to plug that in everywhere I see x. So I have, 1. F of pi is equal to pi times sine of pi. What is the sine of pi? What is the sine of pi? So I wish that I'm still not able to find my unit circle. Pogron, welcome. Pogron says 0. Yeah. So sine of 0, or sine of pi, good job, Robert. Sine of pi is 0, and 0 times anything is going to be 0. So f of pi is equal to 0. Now, I need to determine if the left side limit is equal to the right side limit. So actually, first, before I do that, I will check part 1. So part 1 function is defined, so we're going to put a check there. Next, limit as x approaches pi from the left, because I'm going to be approaching values less than pi, I'm going to use that top one. So I'm going to go ahead and find the limit of x as x approaches pi of x sine x. Well, when I do that, I can plug in my value for pi, and we saw that it's 0. Now, I need to find the limit, or this is still from the left, right, because we're using the top function. Limit as x approaches pi from the right. Now I'm looking at values greater than pi. So here, I'm going to use the bottom one. X times tan of pi x. Well, tangent, remember, tangent of x is equal to sine x over cosine x. And as we said earlier, the sine of pi is 0. Therefore, what is the cosine of pi? It's not going to matter, but just for fun, what's the cosine of pi? George says 1. Right. 0 over 1 gives me 0. And 0 times anything is going to give me 0. Now, does 0 equal 0? Yeah, it does. So, because 0 equals 0, the true limit exists, and we can check off step 2. Now, the third question, does the true limit equal, is the true limit the same as the actual value of f of pi? F of x equals 0. So here, I have limit as x approaches pi of f of x is 0, and I have f of pi is 0. So because of that, that is also true. So I can check it off. And because all 3 pieces have been deemed to be true, this function is continuous. So the answer is going to be yes. And that's it. And with that, thank you, AQ, for the follow. So with that, we will go ahead and call it a day. Thank you, Pogron, for the follow. So, before I go, I'm going to give you my little spiel. You love math. I love math. Helps in life and thinking so much. 100% right. Good night, Pogron. Thank you for joining us. Yeah, I can do integrals, but I'm gonna do those in a different live. But yeah, I'll get to integrals. I already have a couple topics and integrals on my list anyway. Hey, 1 and 3, how are ya? So, no problem. So, I'm going to go ahead and do my little outro here, and then I will call it a day. So, if you want to find me elsewhere other than here, if you go here, this is my channel over there. So, right now I have 2 videos up. I'm currently working on 3 different series, all of which involves calculus right now. So if you could do these 5 things, that would be great. Also, there are a couple other people here on TikTok that I recommend that you follow. First is ACG Math Tutoring. So she is really good at getting people ready for their Accuplacer, their ASVAB, their GED, their TEAS tests, or even if you're getting ready, if you're reviewing Algebra 1, Algebra 2, or Geometry, she is the go-to person for that. And then, Learning with Lynette is awesome when it comes to the abacus. She's actually live right now, and as soon as I am finished with this live, I think she's still live. Let me check quickly. Yep, she is. So as soon as this is done, I will be jumping in there. But yeah, I highly recommend you give her a follow. She's really awesome. MCATs, I'm not sure if Audrey does the MCATs. I'd have to check. If she does, I'll let you know. What is the MCATs? Let me just look at it. Medical college. I'm not sure. I'd have to... ACG still on? Nope. She was on earlier. She'll be live at 9:30 tomorrow night. Or, yeah. Have a good night, George. Thank you for joining us. And then, my last thing is that I offer online tutoring in both groups and one-on-one. So when it comes to group tutoring, I offer tutoring to groups of 3 to 10 students at a time who are all taking the same class. And here, and I'll actually raise my camera up a little bit so that way you can see the whole thing. Here is every subject that I tutor, or everyone that I regularly tutor. Now, if there's one on this list if there's one that's not on this list, it's not because I don't tutor it necessarily. It's because I would need to review the material. So, and the thing is, just because you have to take the same class doesn't mean that it has to be with the same teacher or even at the same school. So if there are 3 pre-calculus students, all with different teachers at different schools, they can still sign up as a group for group tutoring, and it would only cost them $35 per hour per person. And then, I also offer one-on-one tutoring. I'm offering a special right now, where normally I charge $100, but from now until the end of August, if you sign up for weekly tutoring, because this is only a week away, less than a week away at this point, then I will lock you in at $60 an hour. But, like I said, this is a limited time only, because once it turns 12:01 Eastern on September 1st, this offer goes away, and it goes back up to $100 an hour. So if you're interested in either one of these, feel free to DM me, and we will set up a consultation. And with that, I will go ahead and call it an evening. I hope everyone had fun tonight. I know I had fun, because let's face it, math is fun. Or at least for me it is. And I hope, again, that I helped you like math, even if it was just a tiny, tiny percent of the... even if it was a tiny percent that you like math more after this live than when you walked in, then it's mission accomplished for me. Of course, if you like it more, much more, then that's just the cherry on top. So yeah, and with that, have a great evening, everyone. Or should I say morning for me here on the East Coast, because it's 2:02 in the morning. And I will see you all tomorrow at 11:30 Eastern. I think I'm going to do intermediate value theorem tomorrow. So yeah, have a great rest of your evening, everyone, and I will see you tomorrow. Bye now.